All right, so it is Tuesday night, 11:29. Can you guys hear me okay? Okay, John's got it, Julia. Okay, so I assume that that's going all right. So hopefully you might have gotten a chance to look through the video from last night, and that might have cleared some things up, and we can certainly talk about those types of things again as well. But I didn't want to do the exact same thing we did last night again for the people who were joining in. So what type of questions you guys have? And so if this is your first time on, you can either chat in there, which tends to be a little easiest if we have a lot of people asking versus the microphone, since we got a decent sized crowd. So go ahead and ask away. Hold on. Actually, John, you might have just been asking something, and I just turned I had my thing muted. So go ahead again. Okay, so there's one about problem 2 on the most recent homework. So let me see. I've got which one that. Hey, John, can you mic your? I think that's probably yours. Can you mute your microphone while we're going over stuff? Thank you very much. Yeah, so that number 2, we've got, let me see, I don't think I put it on, that I loaded it up previously, but we'll go to a blank screen here. Sorry. All right, so yeah, number 2 is the one where it's got a, we've got the ball and socket kind of like right here, and we had a point A, and then we had this thing on the end, right? And this was going around with a 20 rads per second, right? So it talks about that thing being 18 pound uniform disc, and it's spinning around this axle, right? So there's basically a little ball and socket joint right here, and it's going to spin around this guy with some sort of an omega 1, and then it's got this other omega there, and let's see, this was a Z, and this was an X, and then coming out that way was your Y. Okay? And basically what it's saying is the axle is supported by ball and socket at point A, and it rotates about the vertical axis with that omega 1, and that everything was constant. Okay? So Long, can you guys mute your mic, please? Okay. Thank you. So basically we've got it's asking you to find the value of omega for that thing to stay horizontal, right? So basically we've got omega 2 and an omega 1. So for that thing to stay horizontal, essentially it means that I'm not going to have any omega about the x-axis. Okay. Does that make okay sense there? Okay. And then, as Omar said, we did go over 2 on Sunday, so you can look through that part. So yeah, we can certainly do the axis at point A, right? And then that's the one where we would just use, well, some of the moments about point A is equal to, and we would do our H dot G, right? And this is with respect to our local X, Y, Z. And then we're going to add in plus whatever we choose for our capital omega, HG, and then we add to it R cross MAG. That's kind of really one of those primary ones I've been using all the time, right? Okay, and then, right, for a ball and socket joint, that really only takes in forces. So basically, if I draw out my free body diagram, I'm going to have like right at this point, I'm going to have 3 different forces, right? When I could just call those like an AY, an AZ, and an AX. And then basically this thing's going out, basically we've got this one and we've got some sort of force mg. Okay, does that make all right sense to you? Okay, good. Yep, so we just do there, we figure out that mag, and really the g is just here, so that ends up, that linear acceleration is going to go right back in towards the center, so the mag is not going to have a moment. Okay, so there's a question about integration. So I might, Logan, on there, I probably wouldn't ask you to do a full integration. I could maybe ask you to set one up, right? But I would expect a full workout problem on an integration of something, right? Now, the composite shapes, we did a lot of practice on that, right? So that's certainly fair game, right? We did a lot of these, single axis types of rotations where you have, either bars going out or whatever, but we didn't do, we only did one or two integration type of things, but definitely you should be able to figure out stuff for a composite shape. I muted myself while I sneezed. So we got, you guys got other questions? Okay, so we have two things there. Well, we'll give you, typically we'd give you that type of thing, Julia, and we, I think on, I posted the equation sheet thing, and on there the third page has a bunch of different shapes, right? So that's kind of related to what one of the questions above was, right? Asking about integration versus the other, but in general, we'll give you a sheet that's got the necessary shapes that you would need on it. Okay. Let me check and see, Ben, if anybody else has a question first, and then we'll come back to yours. I always try to sort of rotate things a little bit. Okay, did anybody else have one? The rotating L bar. Okay, so we'll do that one, and then we'll look at the bullet and the plate. So I think I actually have this one on, I kind of preloaded, I think, all of these guys. Let's see. Are you talking about this one, Alex? Yeah, okay. So, and of course, like all these, there's tends to be kind of multiple ways you can do things. But if you look at how it's set up, right, we've got two different rods welded together there at point B. It's got a weight of 2 pounds, and it's got, and bar BC has one of 4 pounds. So if we know that right at the when theta is equal to 0, right, determine the components of the reaction at point C at that location. So essentially, we're looking at it when it's an L shape, right? When it's that. Does that part make okay sense to you? So we're looking at it right here. Okay, so then, right, it's asking about the components at this instant, right? I could have said something like, it starts, BC starts horizontal and swings down, and then you would have to use work energy to figure out an omega, right? But we didn't do that. We said at this location, or kind of like at this instant in time. So what type of problem is this? What's the basic principle involved? Anyone? Is it work energy, right? So Julia is suggesting work energy, right? But that's, I'm saying more like as it reads right now, do I have to use work energy, or am I kind of given the position, right? So momentum would be things where I have an impact or where I have some sort of force through time. And what's our third one? at sort of an F equals MA, right? So if you look back, I got to remember even that's probably like lesson 20 or something. I posted an approach type of sheet that you may want to look back through. So this one really is a Newton-Euler type of setup, so an F equals MA, because it's just asking about the reaction, right? The components of the reaction force at point C at that location, right? When theta is equal to 0, which is the position shown. So it's just asking about one point. There's not an impact. There's not a force as a function of time. There's no two positions, two velocities. So this is just asking for a force right there. So to do that, right, I can set up this guy right here, right? So what are the forces that are acting on that bar? Yep, so we've got the mg. And what we can do is we could go ahead and find the overall mg for the thing, right? So if I've got basically, you know, this part AB, it says that weighs 2 pounds, right? So this part's 2 pounds and this part's 4 pounds, right? So that means then I can figure out what my overall CG is going to be, right? So if I started it, say, from here, then for my X bar, right, that's going to equal sum of the XI MI over my sum of the masses, right? So if I do that, then I end up just having, well, this is going to be, you know, if I look at, say, if I call this bar 1 and this bar 2, then for bar 1, that X, if I'm doing this type of coordinate system, right, then the X is actually 0, right? So that's for bar 1, 0 times 4 pounds, plus for bar 2, that's going to be a minus 0.5, and then times the 2 pounds, right? And I can put G over both of those, but it basically would all cancel out. And then the total is 4 plus 2. Does everybody see what I did there? We're just finding the overall, and did I do that right? I'm just finding the overall CG for the L shape. Well, like I was saying, I could put, you know, if I want, I can put everything over G here, and then that's all going to be over G. So it really doesn't matter. For everything we do, pretty much the center of mass is the same as the center of gravity. Yeah, so Long, you could draw an MA at each of those and then sum the MAs on the right-hand side of the equation. Okay. So then this is, if I do the same thing here, so YI and MI, and then over here I do the sum of the MIs, right? Then that's just going to be something pretty similar, except now I'm going down, so that's going to be a -1, right, foot in the Y times 4 pounds, right? So all I'm doing is breaking these two up to see where those are acting. Right, so then I'm going to do, well, where's my second piece Y located? It's all the way down at 2 feet, right? So -2 feet times the 2 pounds, and then that's all still going to be over our 6. Okay, does that make all right sense, everybody? So basically my overall CG is going to be like at, let's see, that's going to be what, -4 minus, so that's going to be like -8 over 6. Okay, so that's going to be kind of like down that much, so that's going to be down 4/3 is where my overall CG is going to be, 4/3 of a foot, and then it's going to be over this way 1/8 of a foot. Okay, questions there? Does it look like I did that okay? All right, so then the forces, all I've got is, I've got up at this point, I've got a CY and I've got a CX. and then I've got this overall 6 pounds. Okay, and I could have put that force at each of the individual pieces too. Like I could have put the 4 over on the right on piece 1, and then the 2 pounds for the AB part. Okay, questions so far? Okay, and then for my overall kinetic diagram, I can just do everything in the positive. So this would be like an MAG overall X, an MAG overall Y, and this would be an IG alpha. Okay, so that's my FBD and my KD. And sorry, that's a little crowded in there. Okay, so that's my FBD and my KD. So then what are my next steps? Right, what do I do after my sketch? Yep, do my equations motion, sum the forces, right? So what might be a good place to sum moments? Yeah, so C is going to take the most stuff out, right? Then it's going to mean CX and CY go out. But I could have also done it at G, right? So either of those points is valid. But since that's also a fixed axis of rotation, I can now use IC alpha. Now, it would also be fine if you want to use, IG alpha plus the R cross MAG. Right? You get the exact same thing. Okay, but I think this is a little bit easier. You just have to end up using some parallel axis here. Right, so the IC, if I look at it, I've got 2 of those bars. So for CB, right, if I'm doing about C, I actually know that that's going to be 1/3 the mass of BC, right, times LBC. Okay, that's what it is for the first one. Then for the second one, it's 1/12 of the mass AB times L. Sorry, that should be AB. Right, and those are squared. Sorry. Okay, then plus the MAB times the distance squared. And in this case, the distance is going to be between this point and this point, right? So it's between the G of bar AB and point C. Does everybody understand that? So really, I used the parallel axis theorem already on the first term, CB. That's just the same as saying 1/12 ML squared plus MD squared, because D is just L over 2. Do you guys understand how we use the parallel axis theorem to get IC? Okay. Any questions about that? Okay, so then you'll get an actual number there. Yeah, so Ethan, if you just look on where I think it was maybe even 25, then I give you a table. So you definitely get all the ones for IG, right? So you definitely have 1/12 ML squared. But I can't remember if the 1/3 was on there or not. Okay, so from this, like, then what's going to be on the left-hand side? What are my sum of moments about C? So if I look at my free body diagram, what would my sum of moments about C end up being? Yeah, so it's just that gravitational force, right, times the perpendicular distance. So this would end up then being the 6 pounds is my total force, and then that distance we had was an eighth of a foot. Okay. So that's great. Now I have an alpha, right? So does everybody see that I get an actual number for that? So then if I do sum of forces in X equals MA GX, and sum of forces in Y equals MAGY, now I'm going to have the CX and CY in my unknowns. Right? I'm going to end up having the MAGX and MAGY. I don't know what those are. Is it possible to find those? What is AG equal to? So our alpha is part of it, Alex. All right, so let's do the full thing. Yeah, so it's like AC plus, right, if I go to my other part, AC plus omega cross R to G from C, right? And then I have plus alpha cross R. Okay, well, where do I get the alpha from? Right here. What about the omega? Yeah, the omega is given. That's up here, right? And what's acceleration of point C? Yep, so that one's 0 because it's fixed, right? So I know all of this, in which case I'll get a value for AG, right? Because I know the alpha, like I said, from up here, the omega is given. I get an AG. I can plug in the X component here, the Y component there. If I look at my free body diagram, the only force in the X direction is CX, right? So this is just going to be CX equals MAGX, right? And up here, I've got CY minus MG equals MAGY, right? So, boom, I can solve it. That essentially ends up being 5 equations, right, in the end. Okay, and really 5 unknowns because I don't know CX, I don't know CY, I don't know alpha, I don't know AGX, I don't know AGY, but it all falls out because we have 5 unknowns, 5 equations. 3 equations, sum of force in X, sum of force in Y, sum of moments, 2 equations from kinematics. So again, we always do our sketch or our modeling. So FBD, KD, then we do equations of motion, then we do our kinematics usually. Any more questions about this one? Okay, so Ben had asked about this one, right? And so some of the others of you can start queuing up some questions if you want. All right, so for this problem, right, again, I always start out saying, well, what's our basic principle that we want to apply? Right, so what's the basic principle we apply? Yeah, it's going to be impulse and momentum, right, because I have an impact going on. Okay, so what we want to do there is always start out then with our sketch, right? So our sketch or our whatever our model's like. So here we had, right, initially this is going with some sort of an MBVB, and then the block is stationary, right? So then we put in this guy and we do our impulse momentum diagram. So we've got an AX, we've got an AY, right? And then we also have these two that are going to be kind of equal and opposite on the bullet, right? So there's our bullet, and then there's some sort of F delta T, and these should be delta T's too. Sorry, these are hard to see. So those are all delta T's. Okay, and then we do have that mg delta T, but in general we say that's going to be small with respect to our impulsive forces. Okay, and then if I do my part at the end, right, then I'm going to have right in the center there, that's going to be going some sort of, I call that like a capital M times a velocity of g. So that's for the block, right? And then for there, we're also going to have some sort of an I of the block omega. We can call those sort of 2. That's after the impact. And then for these, I would typically say, that mass of the bullet is negligible compared to the full 20 pound, right? So we're talking 20 pounds versus 0.05. Okay, so it's more than 100th smaller. So you could say that part's going to be negligible. If you want to include it, you could put it here and then realize that its velocity is going to be perpendicular to this point right here, right? So that's going to be like an MBVB2. Okay, does everybody understand that slightly unreadable, illegible impulse momentum diagram? Okay, so now you have to decide, well, what point would be good to sum moments about, right? So what point would you want to choose here? Because I'm going to do angular momentum first. Yep, I would agree. So I choose A because you get rid of that AX and AY delta T terms, right? So then I just basically am saying, well, HA1, right? And so it's just 2D now, so it's only about the Z-axis, right, times whatever my sum of moment dt's might be, again, about point A, is going to equal HA at time 2, right? So do we have any sum of moments about A? Right. That answer is no. Those are going to go to 0. That's why we chose point A, because remember, remember what I'm treating as my system is everything together for this. So I'm treating the bullet and the block together, and the impulsive force on the bullet is equal and opposite to the impulsive force on the block. When we say the time, the time just means what it is for. Yeah, I mean, that's all we're going to end up having to use it for. I understand your question now. Yeah, we're going to end up having to use it for part B, and I'll show you what you have to do for that. Okay, so does everybody feel like you could do part A, right? Can you? So basically, this is just a conservation of angular momentum that you do for part A. Okay, because this is going to be just, this first part is just 14 over 12 times the mass of the bullet times 1,500 feet per second. Does everybody understand that that would be h of A at time 1? So that's just the linear momentum of the bullet times the moment arm, right? Because here's the distance right there. Okay, and then for part 2, I can just find I of A of the block, right? Because it is a, right here, that's a fixed axis of rotation times omega 2. Is that all right with everybody? So then you should, if you look up, you can figure out what IA is using, again, the parallel axis theorem. And then you can solve for omega 2. Yeah, so you either do, remember, you can either do IG omega 2 plus R cross MVG, right? So you either do that or you do this one down here where it's about IA. And I've shown you a couple different times how those are exactly the same. Right, so that's going to be the same. right? Because what is r cross mv, right? So if I look at this, then the r distance is just from here to here, right? So that's just going to be like a d, right? And then, well, what's mvg? Well, vg for this is just d times omega. So really, in the end, you get md squared times omega is what r cross mvg is. So you get ig omega plus md squared omega. Well, what is ig plus md squared? All right, that is IA, right? It's just a parallel axis theorem. Okay. So now, how do we figure out part B? Yeah, so there's a couple ways we could do it. We could sum moments about point G, as John's saying, or I could just use linear momentum, right? So the linear momentum system is, and I could even actually do that with just the block as my system, or I could combine the two. Okay, any of those things will work. So basically, I could look and say, well, my MV, and I can do a little summation, right? So my summation at one plus whatever my total sum of forces dt acting on my system are is going to equal my sum of mv2. Okay, and these are vectors. Okay, so that's going to end up being just, in the initial part, that's just that mass of the bullet, right, times that initial velocity, which we said was 1,500, right, and then plus, now we have to look at all those different forces. Well, the F delta T's, right, these guys up there, those still cancel. But now I have an A, and this is in the I hat direction, sorry. I still have an AX delta T in the I hat, plus I have an AY delta T in the J hat. Is that okay with everybody? Right. And it wouldn't be wrong if you put in minus mg delta t in the j hat, right? But just typically we end up saying that amount is negligible. And the other reason is because half the time we don't actually know what the delta t is for a lot of these problems. In this case we do, so it's much easier to throw it in. Yep, since it's a vector equation, you can, we'll just break that up into two different components, just like we did for all the kinematic stuff too, Ethan. So you're absolutely right. We can break it up into X and Y components to solve. Okay, and then for this second part, really, since we said the little m is, the bullet's really kind of negligible, then we can figure out, well, what's the MVG2? Right? Well, what is VG2? Right? And so first of all, that's going to be in the I direction in the end, because VG2 is just going to be that side, like an L over 2 times omega 2. So everybody see what that velocity V2, and remember we're looking immediately after the impact, then the velocity of this thing is just going to be to the right, because I'm just looking at, this omega. It's just a single axis rotation. Okay, so we did kind of two different 2D problems. Does anybody have a question about 3D stuff? Did anybody get a chance to go back and look at the video? Okay, so you said we can start with our initial momentum with the bullet embedded in the plate. I'm not quite sure what you're referring to, Ben. Sorry. Start with our initial momentum. Does anybody remember what he's referring to? Did you mean just tonight, or was this something you're thinking about in class, Ben? Yeah, I mean, I don't think I would have either. I misspoke, or you remembered it slightly different. Yeah, so they become one body in the end, right? Which is right here. But they don't. Basically, it's what are we choosing for our system, right? So what we just did for part one was choosing both of them as part of the system. Now, the other thing you sometimes could get asked is what is the impulsive force from the bullet on the plate? And in that type of case, you would just look at the plate, right? So you would solve it, you'd have this omega, right? And then you could solve the whole thing again, but only look at the momentum of the plate. Because the plate and the bullet are one body, like I say, over here, but they're not at the beginning. Then we're just describing our system, which somebody in one of the sections kind of said, yeah, it's sort of like the, essentially like setting up whatever your control volume is in a thermodynamics or fluids problem. Okay, so changing an axis of an omega, right? If we're doing something like that, we've got, so here's, there you go. So if we have a problem like this, right, then what we're concerned about is it's going to be really difficult to try to figure out what the inertial tensor is for that disk when it's tilted at an angle. So if you're given that x, y, z, right? So what we want to do then is say, well, I'll need to transform this into principal axes. And then in the end, I kind of want to transform it back into XYZ because if I'm sizing a bearing or looking to see what type of forces my bearing can handle, bearings aren't rated according to this random X prime, Y prime, Z prime. It's going to talk about the different side force values that you can get. Okay, so if we were looking at this one, right, then I would have my overall vector for the omega, right? The omega vector is here in the plus x. Does that make okay sense to you? That's what direction the omega is going in. Okay, so now because that was in the x and I want it in this new frame, right? Because basically I'm going to go through and try to solve it all in the new frame. So that omega now, you can really think about it just like this, where here's y prime, here's x prime, right? So this is the y prime and this is the x prime. So I could go through and just figure it out with transformation matrices, but it's also not really that tough, right? So this is our omega here, right? It might be easier for you to just look and say, well, how much of that omega, which we have expressed in our x direction right now, well, how much of that's in the x prime, do you think? Yeah, so basically our omega vector is going to equal omega cosine of beta, right? And that's going to be in this little x prime direction, or I prime if you want. Then how much of that omega is in the y prime direction? Yep, so we've got a sine beta there. But which direction is that? Is that pointing in the y prime direction? It's in the minus y prime. Okay, does that make sense to you, Val, so far? Okay, so now it basically just kind of goes back to those same expressions that we used before. Let me see if I have this. Yeah, so basically it's coming down to here, and since it's really just that single axis rotation, right, we're not making anything change directions or anything. We can now just use this guy here, right? Either one you could actually end up using for this case, but now which one do I want to have you use? Actually, let me take that back. I think it's going to be easier for us to use this other guy. Okay, since we have the G, you can kind of use either one really, but let's use the bottom one because that's going to be a little easier since we already have everything at G. And what you're going to do then is remember right before we just said, hold on, sorry, fix this guy, right? So we had up here, we figured out it's an omega cosine in the x, right? So for here, I'm just going to put in omega cosine, right? So omega cosine of beta, and this is all really, instead of it being like x, it's really xy prime, x prime, y prime, z prime, and it's really kind of what all these guys are going to be now too, right? So we've shifted everything, we're solving it about there. And what was the other nice thing with the inertial tensor? Since we tilted the axes, what did that do for us? For the inertial tensor. Yeah, so we now have principal axes, so that means that goes away, 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 that goes away. Right, so we had an omega cosine beta, and then this was our minus omega sine of beta that we'll put in there, and there's nothing in the z prime, right? Okay. And then I put the same thing in for this other one, so that's going to 0, and then I still have the exact same thing I'd put in. Here would be omega cosine beta, this would be omega sine beta. Okay, and then what's my, if I'm choosing my point, right, I can choose kind of whatever point I want, right? So do you want to choose point A, or do you want to choose G, or do you want to choose point B? In the end, it doesn't really matter, okay, because this term right here is going to be 0 because G doesn't have anything, right? So if I do my FBD, it might end up being easier for me to figure it out over here, right, at point A. Okay, then we need to look, let's take a look at this term right here, right? So the H dot in terms of the X prime, Y prime, Z prime, does it have a value? No, because it's not increasing that spin rate, right? That omega is constant. So this one's going to go to 0, okay, because even though we set our omega to go with both of those omegas, I'm sorry, we set our capital omega to go with both of those little omegas, we don't have the case where it's changing direction, right? The omega vector is always doing this, right? Which is opposed to, hold on for a second, to something like this, where, in this case, the omega 1's making the omega 2 change direction. Okay. Yeah, so if you were going to try to use the top one, right, it's going to be a little bit more complicated because you're going to have to transpose. That's not too bad, right? You would end up having to just use a parallel axis theorem to move it over to axes like right here. Okay, so if you use a top one with the HO, it's not too bad. It's just going to change your I values a little bit. Okay, so any other kind of, yeah, it would be because you've got a distance going from here to here, right? So for all those, you have to use like IXX is going to equal Ixx bar for that disk that you'd find from looking up in tables, plus the my squared plus z squared, and then you have to do the same type of thing for the Iyy and the Izz. And in this case, actually, does our Izz matter? No, because my omega z prime is 0. I don't know. Let's see. You get to choose that, Ben. You choose on there which one. I mean, you can't really make it. What other omega could you use? Hold on a second. Essentially, it is Megan. Megan's asking about what's on the equation sheet. So what it has on there is just I is equal to I bar plus MD squared, right? And the distance is just, if you're doing XX, then the distance is Y squared plus Z squared, right? And then it also has that IXY is equal to IXY bar plus M dx times dy. Yeah, so then for the reaction side, then Ethan, you can do, I'm sorry, Val, you were asking that. There's kind of two ways you can do it, right? The first way is you can figure out, does it make sense that you could figure out what this whole thing is? Right, so if I did that about point A, then I can either figure all this stuff out, and I would have to do out my free body diagram, and I'm going to cheat just a little bit, right? You really need to make it a free body diagram, but with my limited real estate here, I'm going to cheat just a little bit and say, well, what I could do is put this guy, right? So this would be like this would be a force AY, which is really now like an AY prime, right? And then I would have a Z prime. Okay, so, and I would do the same thing over here, where I could do an AY prime, and an, I'm sorry, that would be B, of course, and a B Z prime, right? So I could solve for those because I've got all this thing, right, is in the X prime, Y prime, Z prime. So now I could just sum moments about A, and then it's just going to be the distance over to here. But I think that's a little bit of a pain because of how this thing, you have to figure out what the perpendicular distance is there. It's not too bad. You're just doing still an R cross B. But the other thing you can do, and then you'd have to transform that answer back into X, Y, Z. But probably the easier thing to do is you found all this thing, right, in your X prime, Y prime, Z prime. So then you can just transform it first, right? So either of these methods are fine. You'll get the exact same answer, but this probably is a little bit easier to do. So you get your H dot, that whole thing in the box here, right? So if I'm looking at this entire thing right here, that is my overall H dot, right? That is the time derivative of the total angular momentum vector expressed in the X prime, Y prime, Z prime. If I transform that back into my X Y, Z, the non-prime ones, then it just makes it a little bit easier to figure out, right? So this would be like an A X. This is my, that's not AX, that's AY, sorry. And then I have my AY. What am I doing? Oh, sorry. This is AZ. That's the AY. And then this is BZ. And this is BY. So now if I'm summing moments about point A, then my distance is here, right? And I actually don't remember how long that is, but that would be like a moment caused by the B would be LBY, right? And that would be about the K hat direction, right? So this BY is doing a moment around here, which is about the Z. And then this BZ is going to cause a minus LBZ about the J hat direction. Does that make sense? So this BZ is going to go around like that, and if you curl your fingers around that way, it would be in the minus J hat. So that would be what my sum of moments expression is on the left-hand side of the equation. Is that okay, Val? Okay. All right, so I'm going to try to go find some solutions or at least some answers for the review problems so I can post those up in a little bit. And then I'm going to make this available for looking at the recording. Okay, so any kind of last minute real quick questions? Okay. Well, it's going to be, kind of similar to what we did on the first one. So kind of between 1 and 3, kind of workout-ish, and then between maybe 2 and 4, short answer / concepts. Okay, so study hard, and I will post this video after it goes through kind of all its little conniption things here.